back to the real number system. In this video, we're going to talk about section 4.2. And in this section, we'll discuss prime and composite numbers. So let's get started. First, I want to talk about the manipulatives that we're going to use to represent our numbers. So in this section, we'll use small square chips that we put together to form a rectangle, and these rectangles will represent our number. For instance, this rectangle represents the number 7. Notice that there are 7 small squares in one row. Now, a 7 by 1 rectangle is the only rectangle that we can make using exactly 7 chips. That tells me that the only factors of 7 are 7 and 1. A number is considered prime if the only factors of that number are the number itself and 1. For instance, 7 is prime because the only factors of 7 are 7 and 1. On the other hand, I can have a rectangle as you see below where I have 12 chips put together in one row. This represents the number 12. I can rearrange these chips to make other rectangles, like 6 chips in a row and 2 rows of chips, or 4 chips in a row and 3 rows of chips. Now this tells me that the factors of 12 are 1, 2, 3, 4, 6, and 12. So 12 has 6 different factors. Because 12 and 1 are not the only factors of 12, 12 is what we call a composite number. So a composite number has factors other than 1 and itself. Now 1, by the way, is neither prime nor composite. So many times with working with our numbers, we want to think about what's called the prime factorization. So our composite numbers can be expressed as products of 2 or more whole numbers. This is called the factorization of the number. Now, a prime factorization lists only the prime numbers that are factors of the number. We have what's called the fundamental theorem of arithmetic. This theorem tells us that each composite number can be written as a product of primes in one and only one way, except for the order of the factors. For instance, 6 is 2 times 3. There are no other prime numbers that I can multiply together to get 6. So there's only one way to write 6 as a product of primes. So the fundamental theorem of arithmetic assures us that once we find the prime factorization, there are no other prime factorizations that we can find. So here's how we find the prime factorization of a composite number. We rewrite the composite number as a product of 2 smaller natural numbers. Now, if both of these numbers are prime, then you're finished. If not, we rewrite the composite number as a product of 2 small natural numbers. And we continue this process until all the factors are prime. So let's look at an example. Let's suppose we want to find the prime factorization of 84. Well, I can write 84 as 7 times 12. Now 7 is prime, so I'm going to leave it alone. 12 is a composite number, so I'm going to rewrite 12 as 4 times 3. Because 12 was composite, notice that I crossed it out. I want to look for only the prime factors. Now 3 is prime, but 4 is not. I can rewrite 4 as 2 times 2. Notice again that I crossed out the 4 because it was composite. I want to look at only the prime numbers. So our prime numbers here are 7 times 2 times 2 times 3. This is the factorization. Now, typically, we're going to write the prime factorization in increasing order and with powers. So notice here I have 2 2's, so that would be 2 squared. Then I have a 3 and a 7. So my prime factorization is 2 squared times 3 times 7. You may be wondering, what if I did not start with 7 and 12 as the factors of 84? You can begin a factorization with any factors of 84 or whatever number. So here, if I had started with, say, 2 and 42, I still would have ended up with the same answer. Or maybe you're wondering, what if I rewrote 12 as 2 times 6? Would I still get the same answer? Yes. Remember, our fundamental theorem of arithmetic tells us there is only one way that we can write the prime factorization excluding order. Now, let's look at part B, 495. Remember our divisibility test? This number ends in 5, so I know that 5 will divide into 495. 5 goes into 495 99 times. Well, 5 is a prime number. Its only factors are 1 and 5. 99 is composite, so I rewrite 99 as 9 times 11. 11 is prime, but 9 is not. I can rewrite 9 as 3 times 3. Notice again, I want to be left with only prime numbers, so I crossed off any of the composite numbers after I rewrote them. So 495 is 5 times 3 times 3 times 11. Again, we typically write our prime factorization in increasing order and with powers. So here we'd have 3 squared, because there's 2 3s, times 5 times 11. Part C, 260. Well, 260 ends in 0. By my divisibility test, that tells me that 10 is a factor. So 260 I can rewrite as 26 times 10. Now 26 is composite, so I rewrite 26 as 2 times 13. 10 is also composite, so I rewrite 10 as 2 times 5. So now I have 2 times 13 times 2 times 5. These are all prime numbers. Write your final answer in increasing order and with powers. So we'd have 2 squared, because there's 2 2's, multiplied together, times 5 times 13. Well, what if I want to know how many divisors a number has? I look at the powers. So here, notice we have a p to the n and a q to the m. I want to look at those powers, the n and the m. And notice I add 1 to each of those powers, and then I'm going to multiply those numbers together. If I have more than 2 primes that I'm multiplying together, the same rule holds. I look at the powers, and I add 1 to each power, and then I multiply all of these numbers together. So here, we want to find how many positive divisors that 1 million has. So I'm going to start by writing 1 million as 1,000 times 1,000. Now 1,000 I can rewrite as 10 times 100. 100 is 10 times 10, and 10 is 2 times 5. My prime factorization here would be 2 to the 6th times 5 to the 6th. There are 6 2's multiplied together. That's the 2 to the 6th. There are 6 5's multiplied together. That's the 5 to the 6th. Now my problem asks me how many divisors we have, or how many factors. I'm going to look at the power of the 2 and the power of the 5. So my number of factors, and remember we're focusing on the positive factors here, I look at those powers, and so the first power is 6, and I have 6 plus 1. The second power is 6, so again I have 6 plus 1. 6 plus 1 is 7, and 7 times 7 is 49. This tells me that if I were to list every positive factor of 1 million, I would have 49 numbers in that list. Now don't worry, we're not going to ask you to list all 49 factors of 1 million. Let's look at another example. So here we have 210 to the 10th. I'll come back to that 10th power here in just a little bit. Let's think about 210. This number ends in 0, so I know that 10 is a factor. I can rewrite 210 as 21 times 10. These are both composite numbers, so I rewrite 21 as 7 times 3, and I rewrite 10 as 2 times 5. So my prime factorization for 210 is 2 times 3 times 5 times 7. Now remember, I told you I'd come back to that 10th power. Because 210 is to the 10th power, each of these factors is to the 10th power as well. My problem asks me how many positive divisors I have. So I want to look at my powers here. Remember, we take the power and we add 1 to it, and I do that for each power. 10 plus 1 is 11. And when I multiply 11 times 11 times 11 times 11, I get 14,641. Now, how do I know if a number is prime or composite? Well, I think about this inequality. P squared is less than or equal to n. Now, P is a prime factor. So if our number has a prime factor such that P squared is less than or equal to n, our number, then our number is composite. Now, if I list all the prime factors such that P squared is less than or equal to n, and none of them divide our number, then our number is prime. So here's how this works. So let's look at 109. Now remember, I want to think about all the prime numbers such that P squared is less than or equal to n, or in this case, less than or equal to 109. Now 2 is my first prime number. 2 squared is 4. That's less than or equal to 109. My next prime number is 3. 3 squared is 9. That's less than 109. 4 is not prime. My next prime number is 5. 5 squared is less than or equal to 109. 6 is not prime. 7 is prime. 7 squared is 49. That's less than or equal to 109. 8's not prime. 9's not prime. 10's not prime. 11 is prime, but 11 squared is 121. That's bigger than my number. So that tells me I don't have to check 11. So again, I'm only considering prime numbers, and I'm only considering prime numbers whose square is less than the number. So let's look at these 4 numbers. Does 2 divide 109? No, 109 is not even. Does 3 divide 109? Remember, our test for 3 is we add our digits. 1 plus 0 plus 9 is 10. 3 does not divide the sum of the digits, 10 here, so 3 does not divide our number. Our test for 5 is we look at the last digit. Is it a 5 or 0? No, so 5 does not divide our number. Now, we do not have an easy test for 7, so let's divide 7 into our number. Notice that there is a remainder, so 7 does not divide our number. Because none of these prime numbers divide 109, 109 is prime. Let's look at another example. So let's look at a bigger number, 397. Now again, I want to think about all of my prime numbers whose squares are less than or equal to my number. So here, the prime numbers whose squares are less than or equal to 397. Well, we've already talked about some of these. 2 squared is 4. 3 squared is 9. 4 is not prime. 5 squared is 25. 6 is not prime. 7 squared is 49. It's less than 397. 11 squared is 121. That's less than 397. 12 is not prime. My next prime is 13. 13 squared is 169. That's less than 397. 14 is not prime. 15 is not prime. 16 is not prime. 17 is the next prime number. And 17 squared is 289. That's less than 397, so we'll put 17 in our list. 18 is not prime. 19 is prime. 19 squared is 361. That's less than my number, so 19 goes in my list. 20 is not prime. 21 is not prime. 22 is not prime. 23 is my next prime. Now notice that 23 squared is 529. That's bigger than my number, so I do not need to check 23. The numbers I have listed, 2, 3, 5, 7, 11, 13, 17, and 19, are the only prime numbers, in fact, the only numbers I have to check. If none of these divide my number, then my number is prime. If any of these divide my number is composite. So let's start thinking about the numbers in our list. 2 does not divide 397 because 397 is not even. Add your digits. 3 plus 9 plus 7 is 19. 3 does not divide 19, so 3 does not divide 397. 397 does not end in 5 or 0, so 5 does not divide 397. I don't have a quick test for 7, so I'll divide 7 into 397. Notice there's a remainder, so 7 does not divide 397. Divide 11 into 397. There's a remainder, so 11 does not divide 397. Divide 13 into 397. Notice there's a remainder, so 13 does not divide 397. Divide 17 into 397. Notice there's a remainder, so 17 does not divide 397. One more number to check. Divide 19 into 397. And notice again that there's a remainder, and so 19 does not divide 397. None of these prime numbers whose squares were less than or equal to 397 divide our number. So that tells me that 397 is prime. Let's look at one more. 91. I want to think about all the prime numbers such that p squared, my prime number squared, is less than or equal to my number, 91. 2 squared is 4, that's less than 91. 3 squared is 9, that's less than 91. 5 squared is 25, that's less than 91. 7 squared is 49, that's less than 91. My next prime number is 11. 11 squared is 121, that's too big. 2 does not divide 91 because 91 is not even. Add your digits. 3 does not divide 10, the sum of the digits, so 3 doesn't divide our number. 5 does not divide 91 because the number doesn't end in 0 or 5. Then divide 7 into 91. Notice there is no remainder here. So 7 does divide 91. That tells me that my number is composite. Now, one way that we can find all primes is by what we call the sieve of Eratosthenes. So this sieve lists whole numbers greater than 1, and we sift through those numbers to find the ones that are prime. So let's look at how this works. So here are all the numbers from 1 to 100. Now 1 is not prime, so I'm going to go ahead and cross off 1. 2 is prime, so I'm going to circle it. And I need to mark off all of the multiples of 2. Now you'll notice the multiples of 2 are in every other column. That's where you'll find the even numbers. So go ahead and mark off all of those even numbers. Three is also a prime number, so circle 3. Now I want to think about the multiples of 3. So 3 times 2 is 6. 6 is already marked off. 3 times 3 is 9. So I'm going to mark off 9. Now remember, multiples of 3 means I'm continually adding 3. So a couple of ways of looking at this. As I started, I said 3 times 2 is 6. Marked it off. 3 times 3 is 9. 3 times 4 is 12, and mark off your numbers. You can count every third number and mark them off, or you can think about adding 3. 9 plus 3 is 12. It's already marked off. Plus 3 is 15. Mark off that. Plus 3 is 18. It's already marked off. Plus 3 is 21. Mark it off. Plus 3 is 24. It's already crossed out. Plus 3 is 27. Mark it off. Plus 3 is 30. It's already crossed out. Plus 3 is 33. Mark it off. Plus 3 is 36. It's already crossed out. Plus 3 is 39. Mark it off. Plus 3 is 42. It's already marked off. Plus 3 is 45. Cross it out. Then we'd have 48, 51. Mark it off. 54, 57, mark it off. Plus 3 is 60, it's crossed off. Plus 3 is 63, mark it off. Plus 3 is 66, plus 3 is 69, mark it off. 72 is marked off, 75, cross it out. 78 is crossed out, plus 3 is 81, cross it out. 84 is already crossed out, plus 3 is 87, mark it off. Plus 3 is 90, it's already marked off. Plus 3 is 93, mark it off. Plus 3 is 96, it's marked off. Plus 3 is 99. Then we look at the multiples of 5. Now our multiples of 5 end in 5 or zeros. All the multiples of 5 that end in zeros are already crossed out. I'm going to mark off the other multiples of 5, and they're all in the column below 5. Now 7 is the next prime number. Think about the multiples of 7. So I can say 7 times 2 is 14, times 3 is 21, times 4 is 28, and so on. Or I can say 7 plus 7 is 14, plus 7 is 21, plus 7 is 28, plus 7 is 35, and notice these are all marked off so far. Plus 7 is 42, plus 7 is 49, mark it off. Plus 7 is 56, plus 7 is 63, plus 7 is 70, plus 7 is 77, mark it off. Plus 7 is 84, plus 7 is 91, mark it off. Plus 7 is 98. That's all the multiples of 7. The next number on my list is 11. Now remember, when I'm checking to see if a number is prime or composite, I only have to check the prime numbers whose squares are less than my number. Now my biggest number here is 100. 11 squared is bigger than 100. So what that tells me is every number that's not marked off is now prime. So go ahead and circle the rest of those prime numbers on your list. One last example in this section. Let's suppose that a large toy store carries one kind of a stuffed bear. On Monday, the store sold a certain number of stuffed bears for $1,843 total. On Tuesday, without changing the price, the store sold a certain number of stuffed bears for $1,957. Now we want to know how many toy bears were sold each day if the price of each bear is a whole number. Now the price of the bear is a whole number, so it's not going to be $1.50, it's going to be $2 or $3. I also know that the price of the bear has to be a factor of both 1,843 and 1,957 because the price did not change. From our previous section, we said that if we have a factor of two numbers here, 1843 and 1957, it is also a factor of the difference of those two numbers. So I'm going to subtract. Looking for the factors of 114 is a lot easier than trying to find the factors of 1843 or 1957. That's why I looked at the difference here. So let's look at the factors of 114. Well, 2 is a factor. 114 I can rewrite as 2 times 57. 57 is composite. I can rewrite it as 3 times 19. All of my numbers are now prime, so my prime factorization is 2 times 3 times 19. Any factor of 1843 and any factor of 1957 would also have to be a factor of 114. So we're thinking about 2 or 3 or 19. Well, 2 does not divide either of our numbers because our numbers are not even. That tells me that the price of the bears cannot be $2. Well, if I add the digits, 1 plus 8 plus 4 plus 3 is 16. 3 does not divide the sum of the digits, so 3 does not divide 1843. The same thing happens for 1957. The sum of the digits is 22. 3 does not divide 22, so 3 doesn't divide that number. The only factor that's left is 19. This tells me that 19 has to be the cost of the bear. Now, the problem didn't ask me for the cost of the bear. It asked me how many bears were sold Monday and how many bears were sold Tuesday. So 19 times M is representing the number of bears sold Monday. equals 1,843. Divide both sides by 19, and we see that there were 97 bears sold Monday. 19 times T is representing the number of bears sold Tuesday, is 1,957. Divide both sides by 19, and we get 103. So there were 97 bears sold on Monday and 103 bears sold on Tuesday.